Hypothesis testing, two populations. Mean with population standard deviation not known. So, at the Math Center we are always looking for ways to determine if tutoring is effective. We decided to sample the final grades for students in Stat 50 who came to tutoring more than 3 times, and students who did not come to tutoring at all. From a sample of 50 students in each group, we found the mean score for students who came to tutoring to be 0.85, with a sample standard deviation of 0.02. And for those who did not come to tutoring to be 0.83 with a sample standard deviation of 0.05. Test the hypothesis that the mean score for students who came to tutoring is higher than for those who did not. So step 1 will be to look at the null and alternative hypothesis. The null is indicated by HO sub O, and the alternative is either called H1 or HA depending on your textbook and your instructor. Before I continue, it's nice to think of these as 2 different populations. So we'll call one of them Pop 1 and the other one Pop 2. So population 1, I'll just decide this will be students who got the tutoring for 3 or more times. And population 2 then is students who didn't get tutored. You could totally switch the populations, it doesn't matter which one you called 1 or 2, it's more that you're consistent when you do the problem. So for example, population 1 is going to have some sort of population mean, since we are talking about means here, and population 2 will have a mu2 for its population mean. So when we go to the null and alternative, we're talking about testing the mean score for students, right? It told us to test the hypothesis that the mean score for students who came to tutoring. So that's why we know we're going to deal with means here. For the null, we're always going to have some sort of equality. We're going to start off with the assumption that the mean for the 2 groups is the same, meaning that the mean score for those who got tutoring in population 1 is equal to the mean score for those who did not get tutoring. For the alternative, that's when we bring in what the test is asking us to do. And it wants us to test that the mean score for those who came to tutoring is higher, so that's the key word, than those who did not. And since, step there, we want those who got tutored to be higher, is what we're testing for, we say that our alternative is that the mean score for those students who got tutoring is higher than those who did not. So now let's move on to step 2. And since I'm showing you how to do this on a calculator, that's all we're going to really focus on. You can see my other video on how to do this by hand. So we're going to follow this pathway on our calculator. Stat, test, 2 sample t-test. So we start with hitting the stat button. We click over to test, and then we scroll down to 2 sample t-test. And that's because we use a t-test when we're handling situations where the population standard deviation is not known. And in this case, it's a 2 sample t-test since we have 2 populations that we're comparing. It'll ask us to choose either data or stats. Data is if we had a list, so we'd have 2 lists from the different populations. But instead they actually give us the statistics. They give us the sample statistics, right? The sample mean for population 1 is what we need to know. We need to put in the sample standard deviation for population 1 and the sample size for population 1. Then we need to do the same thing for 2. So all of this we should be able to find from the problem to type into our calculator. So from our problem, we can go up and try to fill in the information that the calculator needs. I like to just go through and highlight all the numbers and then see where those go. So I see 50, I see this 0.85, I see this 0.02, and this 0.083, and this 0.05, so let's see where those go. So it says from a sample of 50 students in each group. So that's our sample size, and it says it's for each of our groups. So that means those are our ends. So we could have 50 students from the first population and 50 students from the second population. That doesn't always have to be the same. In many cases, you might have a different sample size from each group depending on your experiment and what kind of volunteers, participants you could get for that experiment. Let's see what else. Then it says we found the mean score for students who came to tutoring to be 0.85. So that's the mean, the sample mean for those who came to tutoring, with a sample standard deviation of 0.02. So that's our sample standard deviation for that population. For those who did not come to tutoring to be 0.83. So that means that that's our sample mean for those who did not come to tutoring with a standard deviation of 0.05. Great. You could already look at it and see like how likely it is whether or not these population means are equal or one is greater. We could say like, okay, well, 0.85 score versus a 0.83 score, you know, that's a 0.02 difference, right? So you might say, oh, those don't look that different. But you also have to take in consideration the sample standard deviations, because that kind of tells you how much it varies from score to score, and also the sample size, because if the sample size isn't very large, there might be more of a chance that we're able to say that these got to be different or not be different. But let's just run the test. Alright, so I have this up. Let's just enter in our data. And for the last part, we look at our alternative hypothesis to see which way those arrows go. Always pick no for pool for our purposes. Hit calculate. And the two things we're going to pay attention to are the test statistic, the t-score, and the p-value. So let's write those down. So our test statistic, we usually round to 2 decimals, so 2.63, because next to that 2 is a 6, which is 5 or more, so we have to increase the 2 to 3, 2.63. Which means it's about almost 3 standard deviations from the mean, and the p-value, 0.005. We'll round that to 3 decimal places. Great. The next part is to make our decision. So to make our decision, we really just have to remember the relationship between alpha and the p-value, which is called the p-value method, which we're going to be using here. So we look and see, all we're going to check is if alpha is greater than the p-value, or if alpha is less than or equal to the p-value. So what's alpha in this case? Always go up to the problem and see if they tell you some sort of alpha or significance level. If they do not, which I do not see here, we just assume that alpha is 0.05, which is kind of the standard that's used in most research. So let's make that comparison. Well, 0.05 is my alpha. My p-value was 0.005. And we say, well, which one's bigger? In this case, that's what happens. And that means that we have this kind of decision, right? Or a quick and easy way to remember is that if the p is low, the null must go. And our p-value is small here, right? 0.005. And so the null is going to go. We are going to reject it. And the language for that's here is that there's sufficient evidence to reject the null in favor of the alternative. So let's put that into our own words for the final part of this decision. So to state it in our own words, you should kind of just memorize the language here, but then add in what the problem actually means. So in our case, we could say something like, there is sufficient evidence to reject the null that the mean score for students who attended tutoring is the same as the mean score for students who did not, in favor of the alternative, that the mean score for students who attended tutoring was higher. And so notice all I really kind of did was restate what the null and alternative were and put it into kind of my own words. The last thing I'm going to do is leave you with a graph, just so you can kind of visualize what this t means and the p-value means. Because in another video I show you how to do this using the test statistic method, or the traditional method sometimes it's called. And so that kind of looks like this. So t-distribution looks very similar to a normal distribution, forgive my drawing, and so we're going to kind of use that as a basis. So the middle of the t-distribution will still be that overall 0. And that's kind of just your middle point, so test statistics that are to the left of this are negative, to the right are positive. And we can kind of think of the number of them to be the number of standard deviations they are from the mean, where 1 is maybe here, 2 is here, and 3 is, maybe here. So our test statistic is 2.63, so it's probably right around, here or something like this. And it's got this area over here associated with it, and what that area is actually the p-value. So since the t has a different shape, we could imagine maybe this shape is a little higher in the middle and kind of shrinks out, so it's a pretty small area over here to the right. And it's just in general too, the greater your test statistic, the more it's going to be pushed out to the edges, which means your p-value is going to be smaller. And then we just kind of compare that to our alpha. Our alpha over here, since it wasn't given, is 0.05, and which is larger. And so we could think that, oh, the p-value is talking about an area, our alpha is talking about an area this large. So we could say from here to here has an area of 0.05. Sometimes this red area right here is called a rejection region. And that's because anything inside this area here can mean that we reject our null in favor of the alternative, which is exactly what we ended up doing here.